The next tough integral in this series is the integral of x over the square root of x squared plus 4x plus 5 dx. Let's begin. So first things first, I'm going to go ahead and sort of modify the denominator of this function so that I get the integral of x over the square root of x squared plus 4x plus 4, and I'm going to keep that in parentheses for a good reason, plus 1. See, we've maintained the value of the denominator of this function, except I've taken the 1 from the 5, and in doing so I've actually completed the square here. And what I'm left with is the integral of x over the square root of x plus 2 squared plus 1 dx. Now, the reason why I want to do this is because I'm going to end up using trigonometric substitutions to solve this integral. And what that looks like is this. I'm going to let x plus 2 equal tan theta, which means that our x is equal to tan theta minus 2, and when we take the derivative of x, we're left with secant squared theta d theta. Now, in order to complete the trig substitutions, what I have to do is wherever I see values of x, I have to plug in the assigned value here of tan theta minus 2, and wherever I see dx, I have to put secant squared theta d theta, so that now everything is in terms of theta, and I could continue to solve the integral. So this was our original integral, and now I'm just going to go ahead and plug in tan theta minus 2 everywhere I see x, and what I'm left with is tan theta minus 2 over the square root of tan square theta plus 1. In other words, I've taken the x plus 2 and I've replaced it with the tan theta here, and that squared gives us tan squared theta, and we still have this plus 1 that was left over. Everywhere we see the dx, we're going to replace it with secant squared theta d theta, and that's where we get this. Now, I'm going to make use of the fact that our identity says that tan squared theta plus 1 is equal to secant squared theta. Or in other words, this tangent squared theta plus 1 is equal to secant squared theta. I maintain the numerator that I had in the previous part of this integral, and the only thing that's changed is that now I have the radical secant squared theta in the denominator. And I'm also keeping the secant squared theta d theta on this side of the integral. Now, I'm going to go ahead and get rid of this radical sign by reducing the secant squared theta to just secant theta. And what I can do now is I can cancel the secant theta and reduce the secant squared theta to just secant theta by canceling out these terms in the denominator and numerator. And what I'm left with is secant theta, the integral of secant theta times tan theta minus 2 d theta. And this, of course, when I distribute the secant theta, is equal to the integral of secant theta tan theta minus 2 secant theta d theta. Or in other words, when I split these two integrals, I'm left with the integral of secant theta times tangent theta d theta minus 2 times the integral of secant theta d theta. Now, I went ahead and I calculated these integrals beforehand so that we wouldn't spend too much time on this integral per se, but what you end up getting for the integral of secant theta times tangent theta d theta is simply secant theta. And when you take the integral of secant theta d theta, keeping in mind that you have to multiply that by negative 2, what you end up getting is negative 2 times the ln of the absolute value of secant theta plus tangent theta. So our final answer should look like this. Secant theta minus 2 ln times the absolute value of secant theta plus tangent theta plus c. Now, since we want to keep our answer in terms of x, we're not exactly done with this problem. And really our last step is to go ahead and create a triangle. And this right triangle is going to have an angle theta, in which when we take the tangent of that theta, it's equal to x plus 2. And as you can see, when we take the tangent of theta, and tangent of course is defined as opposite over adjacent, we have x plus 2 over 1, or in other words, just x plus 2. Now, it might also be useful to determine the hypotenuse of this function, and when we use the Pythagorean theorem, we find that this hypotenuse is equal to the square root of x squared plus 4x plus 5. So, plugging all this information back into our original equation, if we take the secant of theta, for instance, and then we also find the tangent of theta, which we already have written out here, our final answer looks like this. The square root of x squared plus 4x plus 5 minus 2 times the ln of the absolute value of radical x squared plus 4x plus 5 plus x plus 2. We'll close the absolute value sign, and of course we can't forget our constant plus c.